Hello, I'm Dave Brown for Teletrain. Today's program is part 2 of our discussion of the material in Chapter 7 of your text, Parker Hannafin's Industrial Pneumatic Technology. You'll remember in part 1 we discussed a pneumatic cylinder, its parts, and how it works. We also went over how to determine the proper bore size of a cylinder for various applications. Today we'll be going into greater detail. We'll discuss some things you'll need to know about cylinders if you are designing or redesigning a pneumatic system. As you know, this is a stop tube, and you know from part 1 where it goes in a cylinder, and why we sometimes need one, to relieve stress, especially on the rod gland. Now, to work effectively, the stop tube must be the proper length, and if you're designing a system, you will need to know what that length should be for a particular situation. In order to specify the right stop tube, you'll have to be able to calculate what is called the basic length of the cylinder. This relationship shows that the basic length is equal to the stroke of the cylinder, that is, the actual length of travel through which the piston rod will move, times a stroke factor. The stroke factor is just a number, and it depends in part upon the way in which a cylinder is mounted. You remember in part 1 we showed some of the different mounting styles. Well, all mounting styles fit into one of 3 different groups. As you see here, Group 1 contains fixed mounts, which absorb force on the cylinder center line, like this cylinder, which has a square flange mounting on the cap end. Group 2 contains pivot mounts, which also absorb force on the cylinder center line. This cylinder, which has a fixed clevis on the cap end, is typical of Group 2 units. And finally, Group 3, which contains cylinders that have fixed mounts, but which do not absorb force on the center line of the cylinder. The side lugs on this cylinder provide a fixed mount, but the force on them is not along the center line of the cylinder, so it would fall into Group 3. Okay, so how the cylinder is mounted will affect the stroke factor. It will also be affected by how the load is mounted. A good rule of thumb is that the stroke factor increases as the cylinder and load become less rigid. This chart shows how cylinder style and types of load are related. Here are the groups 1, 2, and 3 we've just discussed. Over here on the chart, you can see there are 6 possible combinations, or cases. And this column contains the stroke factor that should be used for each mounting load combination. Now, notice the 3 types of loads. A load can be fixed to the rod end and rigidly guided during the stroke. It can be pivoted on the rod end and rigidly guided, or it can be supported but not guided. The 3 different types of loads here on the top of our chart are connected to cylinders which have fixed mounts. These 3 on the bottom all have loads that are pivoted on the end of the piston rod, but they are connected to cylinders that use different mounting styles. Let's suppose you have a cylinder with side lug mounting, and it is connected to a load that is guided and pivoted. What stroke factor would you select? Well, a cylinder with side lug mounting, as we've seen, falls into Group 3. And you can see here, Case 2 covers the fixed mount pivoted load combination. So you would use a stroke factor of 0.7. If you had this cylinder and load hooked up in a system that had an actual stroke of 100 inches, the basic length would be the stroke factor, 0.7, times the actual stroke, 100, and that works out to be 70 inches. Being able to calculate the basic length of a cylinder enables you to use this chart. It is called a piston rod stroke selection chart. It shows relationships between the actual load or thrust, the basic length, which we just calculated, and over here, the inches of stop tube that should be used. And you can see it varies from 1 to 7 inches. Let's do an example to show how the chart works for stop tube selection. Suppose you have an application where you calculate the basic length to be 60 inches, and the thrust you need is 10,000 pounds. We go to our chart and locate a thrust of 10,000 pounds and draw a vertical line upward as you see here. Next, we find the basic length, 60 inches, here, and draw a line horizontally across. So the two intersect like this. Now, notice that they intersect in this dark band here, which is the band for 3-inch stop tubes. So to find stop tube length, we use mounting style of the cylinder and load to determine stroke factor. We calculate the basic length, and then we go to the selection chart to pick out the right stop tube length for the amount of thrust involved. Okay, we use this same chart to handle another important design consideration: sizing a cylinder rod for a particular application. What we're worried about here is buckling, or the sudden collapse of a rod during a stroke. Buckling can occur when the rod is subjected to too much thrust, or axial loading. Let's see how to avoid it by sizing a rod properly. Here is the application. We've got a load where the thrust is 1,000 pounds, and the actual stroke is 32 inches. We plan to use a trunnion-style mount on the cylinder cap, and the load we're driving is pivoted and rigidly guided. Okay, so what do we do first? Well, since the force on the rod will vary with different mounting styles, we've got to find out the basic length, and that means we'll need to find the stroke factor, just as we did with the stop tube. A trunnion mount is a Group 2 style, and we've got a Case 6 load, so the stroke factor is 2. If we substitute the actual stroke of 32 inches and our stroke factor of 2, we can calculate a basic length of 32 times 2, or 64. Now we go back to the piston rod stroke selection chart, which we used a few minutes ago. Our thrust is 1,000 pounds here, and the basic length is 64 here. The lines intersect here, and if we go to the next standard diameter, we find we need a rod 1 3/8 inches in diameter. And notice, by the way, that this application would also require a stop tube length of 3 inches. Now let's review what we said in Part 1 about how cylinder cushions work. Let's assume this piston is retracting. This cushion spear moves toward this seat at the cap end. As the cushion seats, it traps air here between the piston and the cap end. This trapped air helps slow the piston and cushions the shock at the end of its stroke. Different cylinders have different cushion ratings, which means that cylinders differ in their ability to absorb shock. And you'll need to know how to determine whether the cushion rating of a particular cylinder will be adequate for the load conditions in a system. But first, here is an important point. When you use this type of cushioning, the maximum pressure developed during cushioning must not exceed the pressure rating of the cylinder. If it does, you may damage the system or possibly cause the cylinder to rupture. There are basically 6 factors which influence the back pressure that will be developed when you are slowing down a load using this cushioning method. How much weight is being moved? The maximum speed of the piston. how much distance will be available for deceleration, the direction of the load friction, and finally, whether there is any initial back pressure in the cushion cavity before cushioning starts. All of these must be considered for critical designs. However, let's take a close look at a few of the more important of them. We'll start by defining what we mean by total weight. There are four main components. First, we have to consider the weight of the piston itself. Then, what is called non-stroke rod weight. It's just the weight of the rod that's still inside the cylinder when the rod is at its maximum extension. Next, we add on the weight of the rod that's outside the cylinder, and that will just be the length of stroke times the rod's weight per inch. And then finally, the weight of the load itself. Let's use an example to show that it's not that hard to find total weight. In this case, we have a 4-inch bore cylinder with a 1-inch diameter rod. The load requires a 30-inch stroke, and it has an equivalent load of 100 pounds. We want to know the total weight. First, we've got some help. This chart can be found in many pneumatic design handbooks, or it is available from the manufacturer. It tells us what the basic weight is for the piston and non-stroke rod when we know the bore diameter, and it gives rod weight per inch when we know the rod diameter. The combined piston and non-stroke rod weight for our 4-inch bore cylinder is 14.2 pounds. The weight for the 1-inch piston rod is given as 0.223 pounds per inch. And since our stroke is 30 inches, we'll just multiply 0.223 by 30 to get the rod weight. So here's our total weight calculation. We add the piston and non-stroke weight, that's the 14.2 pounds, to the rod weight, which is 0.223 pounds, times 30 inches. And then we add on the load weight, 100 pounds. And our total weight is 120.89 pounds. Now another factor we have to consider is maximum piston speed. In most applications where the stroke is over 6 inches in length and the load is horizontal, and where the air pressure is greater than necessary, and there is little friction, we can generally say that the maximum velocity at cushioning will be no more than 20% greater than the average velocity. If you know the average velocity, which is the length of the stroke divided by the time it takes from beginning to end, you can calculate the maximum velocity. When the stroke is less than 6 inches in length, experience shows that the maximum velocity will be no greater than twice the average velocity. This doubling works okay for rod-down vertical applications also. Now let's take total weight and maximum velocity and use them to select a cylinder. This design tool is called a WV graph. The letters stand for weight, velocity, and it can help us determine the cushion rating we'll need for a particular load. You can see that along this axis we've got weight in pounds, and that means total weight. And along the vertical axis is maximum load velocity expressed in feet per minute. The sloping lines give us the required cushion rating for a given weight and velocity. We're also going to use a table like this. They're provided by the manufacturer and give cushion ratings for specific types of cylinders. This table, for example, is for a heavy-duty type cylinder. It shows that a cylinder with a 2-inch bore diameter here has a cushion rating of 14 at the cap end. And if the rod is 1 inch in diameter here, it has a cushion rating of 9 at the rod end. Okay, let's use these two tables to work out a typical problem. Suppose you want to know whether a particular cylinder with a 5-inch bore and a 1-inch rod can be used in a system. Here is what the circuit drawings tell you about the load. The load weight is 85 pounds, and it normally moves at a maximum velocity of 120 feet per minute. The stroke is 25 inches. Can you use the cylinder with the 5-inch bore and a 1-inch diameter rod? First, you'll have to calculate the total weight. The piston and non-stroke rod weight for the 5-inch cylinder is 29 pounds. The rod weight is 0.223 pounds for the 1-inch rod, times 25, the stroke length, or 5.7 pounds. This gives us a total weight of 119.7 pounds. Now you have to go to the WV chart. The maximum velocity here is 120 feet per minute, and the total weight here is 119.7 pounds. The two lines intersect here, which indicates that the cylinder must have a cushion rating of 22.4 to operate properly in your system. Now let's go back to the manufacturer's table for cushion ratings. If we look up the cylinder with a bore diameter of 5 inches, we see that it will give a cushion rating of 26 on the cap end, and with a rod diameter of 1 inch, a cushion rating of 23 on the rod end. Since the load in your system requires a cushion rating of 22.4, and the 5-inch bore cylinder has a higher cushion rating, the cylinder will do the job, so you can go ahead and use it. Up to now, we've been primarily concerned about whether the cylinder we select will withstand the forces exerted on it, forces developed by the air supply pressure and by the load. But when we're using a cylinder to drive a load, we also want to make sure that the rod will move at the right speed. And since cylinder speed is determined by the rate of flow of air into and out of the cylinder, we have to know how much air will be required, so we can be certain that the system can supply enough flow. The flow rate required by a cylinder is based upon how much air is needed to move a load at a specified speed. Now, moving the load requires filling the cylinder with air. And if we need to do this in a specific amount of time, say 2 seconds, what we need to know is how much air flow it would take to fill this much volume in 2 seconds. This formula tells us that the volume of a cylinder is the area of the piston, A, times S, the piston stroke. Do you remember how flow rate is measured? Well, it's in standard cubic feet per minute, or SCFM. Now we know that a cubic foot of air can be at various pressures, say 15 psi-A, 50 psi-A, or 100 psi-A, and that the air will take on different volumes depending upon how much it is compressed. No matter what the pressure, it is still referred to as a standard cubic foot of air, because that's what it is under normal conditions. But as we compress our standard cubic foot, it takes up less and less space. Now, since the air flowing into a cylinder will be compressed, it will take up less volume than air at standard conditions. The higher the pressure of the air in our system, the smaller its volume will be, and the more SCFM it will take to fill the space inside the cylinder. So we will have to calculate what is called the compression ratio of the cylinder. It accounts for the decreased volume of air at increased pressures. As we can see from this formula, the compression ratio of a cylinder is equal to the absolute pressure inside the cylinder divided by the absolute pressure outside the cylinder. Once we know the volume of the cylinder, and the compression ratio, we can calculate the flow rate into the cylinder. Here's how they're related. Basically, the flow rate in cubic feet per minute equals the cylinder volume times the compression ratio here, divided by the time it takes to fill the cylinder, times a constant, 28.8. Let's suppose we had a cylinder with a 4-inch bore. As it extends, it pushes a load of 628 pounds, a distance of 42 inches, in 2 seconds. What must be the flow rate into the cylinder? Well, first we have to determine the air pressure at the cylinder. Since the rod is extending, air is being supplied at the cap end of the cylinder, and we will assume the exhaust pressure at the rod end is 0. So we use this formula. The force exerted by the rod is 628 pounds. And we've substituted the area of the piston. It's 12.56 square inches. By dividing, we find that the air pressure at the cap end must be 50 psi. We also need to know the cylinder volume. It is the piston area times the stroke, or the 12.56 square inches times the stroke of 42 inches. The cylinder volume, then, is 528 cubic inches. Now, as we've said before, the compression ratio of the cylinder is the absolute pressure inside the cylinder divided by absolute pressure outside the cylinder. In this case, 50 psi plus 14.7 equals 64.7 psia inside the cylinder, divided by absolute pressure outside the cylinder, which at the plant site at sea level is 14.7 psia. And as you can see, the compression ratio turns out to be 4.4. We're now ready to calculate flow rate, and we've substituted the values in this equation. The volume is 528 cubic inches. The compression ratio is 4.4. And the time in which the rod extends is 2 seconds. The 28.8 is a constant. So if we want this particular cylinder to move the specified load through the 42 inches in the required 2 seconds, we've got to have a supply capable of providing a flow rate at the cylinder of 40.3 standard cubic feet per minute. Well, you can see that it's important to use the right cylinder in pneumatic applications, and that it involves more than just picking one off the shelf. Often you must consider stop tubes, rod diameters, and cushion ratings to be sure you've chosen the right one. And the system has to provide enough air at the right pressure to enable the cylinder to do its job. This concludes Chapter 7 of Industrial Pneumatic Technology. Your review exercises are on page 80 of the text. I'm Dave Brown for Teletrain.